Okay. Okay, while they're figuring that out, I'm just going to quickly introduce everyone. Maurice and Uli, they're actually currently inside one of our clean rooms. It's the SNF Clean Room, the Stanford Nanofabrication Facility. And then I also have Mr. Jay Tower, who is also here, just to give you an overview and sort of talk about what it's like to be inside of the clean room. I hope you remember from earlier today, we were talking about all the sort of engineering controls that it takes to make something at the nanoscale. We also have to, so we're inside the building or the room that we do a lot of the fabrication. And then obviously we also need really awesome staff. And Maurice, Uli, and Jay are those staff members who help the students do a lot of the research, make sure the tools are running properly, make sure the students, a lot of the graduate students or postdocs or researchers are getting trained appropriately. And there's a lot of stuff when it comes to safety, making sure we're safe when it comes to working with dangerous chemicals and things like that. Okay, all right, Uli. We good?
Because she can hear you now, so she's happy.
Okay. What happens if I spotlight the video?
You can put it right there.
Okay. Oops. Yes, I see you, Uli. Can you talk?
He wants to hear your voice.
Can you hear me?
Yeah, and you. Oh, but you know what? I only hear the one from Maurice.
I wonder if this one is she muted?
Yeah, she's muted, but her sound is on. Okay.
Okay, can you
yeah.
talk now?
Yeah, I can hear you, Maurice.
Perfect. Okay, so let me pin, I'm going to spotlight all your videos. I hope that works. So anybody, tell me if the spotlighting works or doesn't work. Another thing is because we're having certain precautions for COVID, they're trying to block off, I think, a part of the clean room because so no one walks in because we have a certain number of density quotas. Okay. All right. Are you guys ready to talk? Okay. Who's going first?
Hey.
Okay, Maurice is going first.
Okay, I'm ready.
Okay.
Hi, everybody.
Everyone is waving. I don't know if you can see. Everyone is waving. And we're waving back. Yeah.
So we have to go away. Ludwig needs to get in here, Maurice.
Okay.
But keep talking. We'll keep going. Who cares about Ludwig?
Okay.
So this is the issue, Angela. I said we might have to get out of people's way.
Yeah.
But keep going.
Okay, well, where are you guys right now? What's happening?
So what's happening? So we came in especially for this. As you said with the COVID thing, you're trying to minimize how many staff are in the lab at any time so that the users can use the lab. Ludwig, who just came in, he's getting ready to clean some wafers in this bench right here.
I have to go away now.
Okay.
Where do you want to go here? Go the other way. So this is the difficult part. I had two people coming and it's like I had to say no. They found another aisle.
Okay, good.
So it's not easy.
Yeah. So
So,
go
go ahead. I'm sorry. No, go ahead.
Well, I was gonna bounce around some of the places, but if you guys want to just stick to the one area, that's fine. But I just want to give you guys an overview, like a big picture overview of all the different tools. There's hundreds of tools inside of this clean room, and this is also where you would enter the clean room. This is where you would gown up. And then once you're gowned up properly, just like where Maurice and Uli are, then you can go in. And now people are wearing masks. Usually you wouldn't have to do that, but because of COVID, obviously, we are doing that now. And then, I don't know, Maurice, what did you have something to add?
I was going to say that, yep, we are wearing more than we normally do. That I don't know what they know already, but normally we do wear the bunny suits, and that is so that any particulates that are coming off our body, our clothes, or anything like that doesn't destroy the research that we're trying to do. We do wear even more protective gear. At this wet bench here, we do a lot of cleaning of things, and we do use acids and bases to clean things so we can take off contaminants. So we may end up putting another layer, a apron on, chemical resistant apron. I'm not going to put it on. And another pair of gloves on top of this, and a face shield on top of this, so that we could actually use the wet bench. So that's what Ludwig, you see him right there, the back of his head. He's going to be doing that in a few minutes, cleaning wafers.
Right here. Yeah. A big part is, when we have these wafers, do you guys have any wafers by any chance to show?
Sure.
I thought you might have had them. But these are the silicon wafers that I was talking about. I'm gonna stop sharing my screen for a minute, and I will spotlight Maurice's video so he can show you guys. But these are the wafers that I was talking about. Can you see him in particular? Yeah. So he's actually holding up a blue wafer, and we were talking about the different oxide colors, right? So this one is blue, and I remember it correlates to a certain thickness, but right now I cannot remember. I don't know if anyone can remember.
This is going to be somewhere around 1,000 angstroms. It's not quite 1,000, but it's going to be somewhere around 1,000 angstroms.
So that's about 100 nanometers in thickness. Okay. And these are the wafers. So these are 4-inch wafers. There's all different types of sizes of wafers. But this is what we primarily use in our clean rooms for something that's more research based. So, and Jay, feel free to chime in too. Jay was actually, was once a former high school teacher, by the way. So he has been there. Okay. Yeah. Maurice is showing more wafers.
Keep talking, Jay.
Okay. Yeah. And go ahead, Jay.
Just tell me whenever you want.
I don't know. Do you want to talk about high school, coming from high school over to working in the clean room a little bit?
Yeah, sure. So hi, I'm Jay Tower. My family and I are originally from Massachusetts. I sort of got into physics when I was looking for a second career, and it wound up being teaching. I left a career in recording studio work, actually, and then wound up going back to school and getting a degree in physics. I started teaching at night while I was doing that, and I fell in love with teaching. So I taught high school physics for 6 years in Massachusetts. That led to an opportunity to go to graduate school. And so I did that. I left teaching to do full-time grad school. And while doing that, I had the chance to work in a clean room back east at one of the NNCI facilities at Harvard called the Center for Nanoscale Systems. I was a student at UMass Boston, but we used the lab at Harvard because UMass Boston didn't have a fab. So I learned fabrication techniques during grad school and sort of fell in love with the clean room. When we relocated out here to California, I taught 2 more years of high school, down in Gilroy before the opportunity to work at Stanford came along. And so now I do, well, one of my duties is safety training. I work at another lab, not at SNF, but at SNSF, which is sort of a sister site in a different building. It's a small room, but people still do fabrication there. I train new users on lab safety things, procedures for using the various tools, but also chemical safety. And, myself and 3 other staff members keep our little fab running. And it's very interesting. I never would have expected to wind up in a job like this. I do miss teaching, I'll tell you that. I miss the classroom a lot, but you know, for over almost 12 years of teaching physics in various aspects to high school students, it was time I was ready for something a little different. And I do get to still interact with students, which is nice. Mostly grad students, which is, you can probably imagine, a little different than teaching. But it is an interesting role, and I do feel very lucky that I can apply the things that I learned in graduate school at work now, and not in the fashion that I would have expected, but I like the fact that my job sort of combines teaching and clean room work in an interesting way. I don't know what else you might like for me to say about that.
Yeah, that's good. Okay, so Maurice and Uli, do you want to sort of show around the clean room if you can?
Yes,
How hard would that be? And
How do you want to do it? Do you want to do it on the cameras up there, or do you want to do it on the camera that Uli has?
I will. Why don't I follow you around the cameras and you guys can talk, and I'll share my screen as well in
Should
case
we go
you
in the
can.
little area then?
Okay.
You go.
We're gonna go
Okay.
into the little area.
Because yeah, so for context, I gave them an overview of litho, but I think there is some stuff that can be filled in. And also, I'm sorry, everything is so chaotic, but I think this is just what we have right now for tech. It's a little limited. But I'm gonna highlight one of their videos. So this is Uli on their screen, so you can watch my screen, but you can also watch their video. Display. All right, let's see where they are. Okay, they're over here. Okay, I see you guys.
Which camera do you see us on? That one? Or
Yeah, that one.
That
The
one?
Yeah.
Should we walk over there?
No, I'll come to you. Hold on.
Okay. Hey,
Hold
can
on,
I
I
do
gotta-
why it's yellow in here?
Sorry.
First of all, is it yellow in here?
Oh yeah, why is it yellow in here? Remember? This was a question I asked you, but I didn't give you the answer yet. I can't find you. Okay, I don't have access to that camera that you're talking about. So I have the hallway camera.
Can you see me now?
No. Oh wait, yes. Yeah, it's by the door. Oh, can I tilt it? Yes, I can. Yeah, I can tilt it. Oh no. Okay, let me. Yes. I'm moving.
Oh, there we go.
There we go. Okay.
That was quick.
Yeah. Okay,
So
so
did they say why it's yellow in here?
yeah, does anyone have any guesses of why it's yellow? Feel free to put it into the chat because I know it's a little chaotic right now. Okay, let's see. Someone says to filter the UV lights. They got it in one.
I like it.
Yeah, that was Usha. Thank you.
Bravo. So we use white light in here to expose. We use white light in here to expose things on our wafer, on the photoresist. So we have to filter out all the white light. So we use the yellow light so that we can actually see inside. So this is like if you were inside of a dark room, if you're doing traditional photography, except that instead of using a red light or being in total darkness, we're using the yellow light. The chemicals that we use, the photoresist that we put on for patterning, it is sensitive to white light. So once we put on the photoresist onto the wafer, we will expose specific areas on that wafer using white light. So it could be either in a stepper or contact aligner or with a direct light system or an E-beam system, and we can expose the photoresist in patterns in the areas on the wafer that we want. Is that a good general explanation, Angela? Uh-oh.
I'm sorry, I'm muted. That's good. But actually, one thing I wanted to point out was, so to your right, I think, is right the spin coater. So that's where you would put that light sensitive material on top of your wafer. That's kind of the same thing as the blue paper. That's how you make it light sensitive, by putting that blue stuff on there. But over here in the lab, this is where you would spin coat. It's kind of like, do you ever remember that splatter paint activity that you would like spin it really quickly and pour paint on? It's actually the same concept. So this round thing over here, it kind of looks like a metal donut, would spin really, really quickly, and then you would pour this polymer on top and then bake it so the vapor would evaporate. And then once you were done with that, you would actually move. Do you guys want to walk over to the contact aligner?
You want a contact aligner? Okay.
Yeah, one of the aligners, one of the exposure tools, and then you would expose it. So just like we did that with the UV light, we put it out in the sun, right? So they're moving over here. I see them in front of the ASML.
You want to keep going into the contact aligner?
Yeah.
Yeah, do I have visual on a contact aligner? I don't.
And that's fine. We can check it later on.
Oh, here, I see. Yes. I have it. I have it by the, well.
If you take Maurice's camera.
Can you see my camera now? Right now we have somebody that's actually doing it on live.
I will highlight this video.
We're giving a tour for a remote tour for middle school teachers.
I'm going to stop my share. Can you guys see Maurice's video in particular?
Well, you're not supposed to look.
What?
You're not supposed to look in the UV light.
Oh. Okay.
What do you see now?
You see, can you guys see what's going on? If you right mouse click over Maurice's screen, you can pin the video so you can make it bigger if you want. But yeah, you can see the actual contact aligner going down and closing, right? And then on the screen, on the CRT, the cathode ray tube screen on the right side, you can see that it's exposing a pattern. Oh, and then that's where the wafer goes. They just pulled out that little tray. Do you see that here? Are they taking it out? Yeah, they're taking it out. Very cool. Thank you. Yeah.
And now she's not yet inspecting it, but the next time.
Where are we going?
Angela, where should we go now?
Where do you want to go, Angela?
Where should we go? Jay, where should we go?
What is it that they want to be able to take back to their classrooms? That's what.
Yeah, what do the teachers want to see is actually a better question.
Oh, yes. Or what do you want to see, or what do you want to ask us?
Yeah.
They know too much.
Yeah, I guess so.
What will you use the wafers for?
So the wafers, depending on what users are trying to create, it could actually be just a base or a substrate and they build up on it. If they're building like a MEMS type device, or if they're doing something electrical, you're building a circuit. That may be actually part of the circuit that you're building. So it depends on what you're building. That's the nice thing about this equipment set and the wafers themselves is that depending what you're building, you can be very flexible on how you actually use the wafer. So again, some people are just using it as their base and then they build up on top of it. And then other people, the wafer is actually used in the electronics of the device. So it a lot of the questions you guys are going to ask me, my answer is going to be, it depends.
Yeah. Okay, we have a couple questions. Samantha asked, could we do this with our classroom? And yes, 100% yes. And we will work out the technical difficulties. This time around, it got a little complicated because a lot of space limitations, but we have done it before over video. So we definitely do remote field trips. Amrit asked, what is the wafer made of again? And then Vicky also asked, what is the temperature in the clean room and what type of air pressure is used to keep it clean? So lots of good questions.
Okay, so number one, most of the wafers are silicon wafers, but we do have people that are using silicon germanium, using sapphire, using gallium arsenide. So it depends on the properties that you want for your actual device. But most people in here are using wafers that are silicon based. What is the temperature inside the fab? Is that one of the questions?
Yeah, what's the temperature inside the clean room?
In the clean room. So it's a little bit cooler than what you consider room temperature. It does get warm wearing these, so we have the temperature just a little bit cooler than a normal room temperature. And in the summertime, we tell, in the wintertime, you know, when it's cold outside, people generally want to wear something, sweaters or things like that. We tell them, don't wear that in here because, again, it's not going to be cold in here. We keep the temperature and the humidity constant all the time. The chemicals that we use, the photoresists, are very dependent on temperature and on the humidity. So one of our biggest expenses for the lab is temperature control and humidity control. We have to keep those things fixed because the photoresist has a very limited temperature range that it'll work.
Mm-hmm. Very good. Okay.
And you had one more question?
Oh, the air pressure, right?
So the air pressure. So we're in a positive pressure. We have air blowing on top of us. If you can see the ceiling, you can see that there's holes in the ceiling. This is actually a giant HEPA filter inside here. All the volume of air in this 10,000 square foot is filtered every 8 seconds. So every 8 seconds, the whole volume of air is filtered. So we have air that's being blown down on top of us, and it actually goes off into the sides. Let me show you something. So from the ceiling and then down to the floor, and if you look down, let me go over here. The walls don't go all the way to the floor. The wall ends here, and the air actually goes back underneath there, and then back up to be filtered again. So that's part of the reason we can call this a clean room or an.
Oh, you muted yourself. I don't know how that happened.
Oh no!
Okay, you're back.
So that's one of the ways we can keep it very clean in here and build very, very small parts, is that we are constantly filtering the air.
And we hope that the virus sounds good.
And also, this is, as we believe, and it hasn't been proved yet, we think we're one of the safest places for corona because things aren't going to go this way with the air that's coming down. It's constantly taking everything down to the floor and then going through HEPA filters.
Yeah. Oh, Amrit has a good question. Do you have a favorite machine? Maybe Jay, Maurice, and Uli can say, you know, their favorite one.
Uli, what's your favorite machine?
I have a favorite machine. It's a white light sensitive instrument, and I can see the feature sizes. See the white light interferometer.
Is it the key?
So yeah, similar to Kien's. So the fun thing is you get to see sometimes the finished product, what the students are doing, because we are not making any wafers or any devices.
Jay, what's your favorite tool?
Who, me?
Yeah.
Oh, well, when I was building devices, I spent most of my hours on a contact aligner doing alignments by hand, but I guess I have to say that's my favorite because there's as much of an art to getting it right as there is anything else with a contact aligner.
like this one.
Yeah, that's what Lisa was doing over here. She was on the contact aligner over there aligning wafers.
Yeah, doing it by hand takes some practice. So when you get good alignment by hand, it's pretty satisfying.
And for me, my favorite machine, I would say, I'm a deposition guy, so I deposit using furnaces or a sputtering tool. I have a metal deposition tool, and I can deposit all types of metal. So anything from palladium to platinum to gold to aluminum. The nice thing about this is it's relatively quick, and I can see the results. Some of my other tools, like the furnaces, it can take hours before I can get something that's thick enough where I can actually see it. So it's if you're like me and you want instant gratification, then the metal deposition tools are the way to go.
Okay, we have one more question from Vicky. Are there any other special cleaning processes used using a clean room?
Wow. So yes, and we do lots of cleaning, and not only for taking off contaminants, but also for taking off different layers. So there are wet cleans. We have cleans that are done in other tools like plasma related tools. So we have almost as many ways that we can deposit things. We have cleaning or stripping ways of taking it off. So if you say that we have 50 ways of depositing things, I will say that we have 48 ways of taking it off.
Okay, awesome. Thank you. Do you guys have anything to ask? Okay, yeah, Jenny has a good question. What are some examples of research taking place and for what purposes? Like any sort of real world connections?
So this is the thing that is kind of neat about working at Stanford, because we work with some of the best and the brightest in the world. And it sounds like we're bragging, but these people are doing all incredible kinds of stuff. So we've got people that are working on artificial retinas. You have people that are working on cancer detection. You have people that are doing all kinds of things that have to do with energy. So energy scavenging. You have people that are doing solar detectors. Almost anything that has to do with the sciences. We have all people that are making all kinds of measurement devices that may go on the wing of an aircraft or go off into space. We have people that are making circuits that can go to very harsh environments, go to Mars or to the moon. So we've got people, and in almost any of the sciences, we have people here that are working on something using our equipment set to build something that they can do. Some of the question people ask is, well, what has come out of the lab that we may have heard of? Probably the biggest thing that people have heard about is Bosch did some of their early research on airbag detectors using devices that were built here. So that's one of the other things. There are a lot of people that are doing stuff in here, and there are things that come out of here, and sometimes we never know what they're actually doing. We have students that are working here. We have industry that's working here. We have startups that are working here. The students are pretty open about the research they're doing, but the industry and the startups, generally, we don't know what they're working on, which is okay. It's their research. As long as they follow the rules in the lab, we're okay with that. So
only research is allowed.
Yeah, so people are allowed to do research in here. They're not allowed to do actual production. So proof of concept things are done here. We've got 2 or 3 companies that are doing building displays. So there is a fruit company. We're not allowed to say who they are. We don't talk about the fruit company, but they were doing some research on displays, and they were using this lab.
Okay, thank you, Maurice. And then Jay wanted to add, there's also a big push, obviously, for COVID-related research. So Jay is mentioning a group at SNSF that's working on a rapid antibody tester on a chip. And so remember day one, so long ago, I was talking about lab on a chip and that whole thing with Theranos. That's kind of, the whole concept of lab on a chip. Theranos was using, but we also use it obviously here and now because it is just a sort of nano microfluidic related concept, but it's good for cheap and fast testing. So people have been leveraging that as well. Yeah. Do we have any other questions or comments, or do you guys want like more video feed on all the different sections of the lab? Anybody? Okay, Amrit, do you make the wafers in the lab? Oh, that's a good question. We do not. Oh, and then Fiaz asked, what is the procedure to use your equipment for conducting experiments? There's a lot of procedures. So I will say for research, and Maurice, maybe you can comment, or Jay or Uli, when you get your PhD, I would say at least 20 to 30% of your work is just figuring out how to use the tool, if not more. It really depends on your project and your research. So it takes a while to really get to know some of these tools. Like each of these tools had to be invented by somebody or a team of people to become invented and understand how it works, what are the properties, and then actually to optimize that for your own project. So it takes quite a long time. And then Maurice, you want to talk about how or if we make the wafers in the lab? And then Dustin asked, how fragile are the wafers?
So we don't make the wafers in the lab. Wafers are, for the most part, they're a commodity that we can buy and then people build on top of it. Occasionally, people need very, very specific types of wafers or specific doping, and they can be modified here, or they can be at the manufacturer. You can specify something, but we don't make the wafers here. We're mainly just building the devices after that. The wafers in general are very fragile. So the wafers are thin, and depending on how thin they are, they can be very, very fragile. They're very sharp. Silicon is not something you want to cut yourself with. So we are very careful with them. When I first started in industry, one of the hardest things I had was just handling wafers without breaking them. When you're first fully shaking your head, but it is incredible how difficult it is when you're first starting out. But then after you've done it for 6 months, it is actually very difficult to break a wafer once you're used or your hands are calibrated to doing it. So generally, you don't break them when you're doing stuff. Machines may break them, or you may actually drop one and break them. But in the handling, after you've done it for a while, it's very unusual that you break a wafer. But they are pretty fragile.
I have just a follow-up question. So if I have an idea and I want to use your electron microscope, where do I submit my request for using that?
So we have a procedure pretty much where we are open to anybody who has an idea. So on our website, you can basically fill out all the paperwork. There is a fee, so we make our money, or we pay for the staff by charging you per hour to use the equipment. So there is a charge for it. But basically, we're open to anybody who has an idea and is willing to get trained on the equipment to do it. So you have to fill out a bunch of paperwork. You have to get trained on safety procedures in the lab, and then you get trained on the specific piece of equipment that you want to use. So there are a lot of hoops that you have to jump through to do it. But if your research is important to you, you will jump through the hoops.
Yeah. And actually, yes, that's a good point. So for tools, we do have people that are going to, we're going to have some tool demos tomorrow. So we're going to work with UCSD to do a remote SEM session, a scanning electron microscope session. And you can ask them to take a look at your samples, I believe for free. And then there's also a program with Hitachi where you can do a lot of sample looking at. And then, so does that answer your question? Yeah.
Yes, thank you very much.
Yeah. Good. All right. Do we have anything else to add? Because I feel bad. I think Maurice and Willie have just been running around the lab.
We're just trying to get out of people's way. That's all.
Yeah. So I want to try to limit that amount of time. Okay. If that's good, I think we'll end here. If anyone has any other questions, and obviously, if you have questions, I feel free to email them to me, and I can always forward them along and try to field them too. Okay. So, other than that, thank you,
Angela. If anybody wants help developing a lesson for their classrooms, get me in touch with whomever. I'd love to help do that.
Okay. Yeah. Maybe you can come by because they're all gonna present. They're all going to present.
Okay.
I know you guys don't, some of you are, there's varying degrees of happiness, but they're all going to present Thursday afternoon on sort of a rough lesson plan that they're developing throughout the next couple of days.
Yeah, cool. I'd love to help with lessons and labs and stuff.
Okay, I'll invite you for the afternoon.
Okay, awesome.
Okay, all right, thank you, Jay. And then thank you, Maurice and Uli. Okay, yeah.
Bye.
Okay, bye. All right. Oh, big thank you from Leo. Okay, awesome. All right. Okay. Okay. Alrighty. So we're back to normal. Sorry, it was so chaotic, but I hope that was sort of interesting to sort of get a sense of what it's like inside the clean room. You can tell there's actually, the reason why it was so loud in there is all the machines are running at once. There's a lot of vacuum being pulled because a lot of the stuff being done is, you know, very clean. So everything needs to, all the chambers have to be pumped down. And so that's why there's just so much noise. And that's actually why they wear headphones, is because they have the noise canceling headphones. They're probably not listening to music, but they're actually just to cancel out the white noise that's going on. Okay. And then I just wanted, I don't know if you guys got a chance to actually see everything that's going on, but this is the one of the wafers. I actually laminated this one just for safety because yeah, if it does break, it will shatter. And actually it's shiny like a mirror. And this is a silicon wafer. It's super shiny, it's crystalline, so it's a single crystal. And I can get into this a little more and I can add more information about it. Because I do have tons of references on how a silicon wafer is made, but it's a perfect crystal. So it comes out in this like wide log. It's called a boule, and it's one big crystal. And they actually, it's this really cool method where they seed the crystal and then they slowly turn it. And the reason why they turn it is because they're trying to counteract the Earth's rotation as the crystal is being formed. Because they realized like, and this is a technique that was invented like a very long time ago. And they realized that the Earth's rotation would sort of impact the growth and atomic arrangement of the crystal. So they have to turn it basically the opposite way in order for it to become a perfect crystal. And then I just want to show a few more cool examples that are going on. This one is gold coated with some like a little pattern on top. You can kind of see it's little, it might be a little hard to see. And then we also have this one. It's actually coated in that photoresist that I was talking about. It's actually red, and it is kind of a plastic material. It's almost like like a laminated kind of feeling on the plastic. And then something that's fun. So not everything is super tiny, like you can see here with the tiny little dots. Some things are kind of fun where you can actually take a transparency, like a negative, and develop it. So this is like the front lawn of Stanford that they printed on a wafer that I thought was kind of fun to show. But if you actually feel it, I wish you could, because usually I pass these samples around, but you can feel it and it feels totally smooth. But the reason why it's two different colors is because, you know, we etched part of the blue away. But you can't actually tell the difference with your finger, okay, because it's so small. Here's another example with the Stanford seal. We got to represent, obviously. And then finally, this is like a cute little device. But what I wanted to point out, like you can get really close. They're really tiny, tiny patterns. And this is just, you know, visually with your naked eye. But you can actually see tiny, tiny patterns. And this was created inside of one of the clean rooms. So I thought it was a nice example to show. Okay. All right. So we're going to switch gears again. Never a dull moment. So we're going to